Hey, math people, this is a big day, big lesson, the chain rule, really fundamental move of differential calculus. So we're on that chapter. We're going to be looking at the intuition behind it, practice identifying when to use it, and then we'll spread this up into rounds. So you can read here, but I'll read for you. We got polynomials, then we'll do radical rationals, then some trig, then a little bit of product quotient involved as well, and then round 5 is a lot of fun. So be sure to click into that. Remember, this video is for you, Kylie, or whatever your name is, right? So the point is to pause when you need to, use the chapters when you need to. This video can be for you if you use it correctly. So let's math right now. All right, so warm up. Just differentiate, right? Looking at these two functions, the derivatives should come out quite nicely. See if you can do them. 3, 2, 1. All right, so there's two methodologies for each, which is why this chapter is a little fun, is because we have different methodologies that could render the same result. So I'm going to show you a third method for each of these. But if you look at the first one, what I did was I wrote it out twice, and then I just did algebra, right? So I did not do what's called the freshman's dream of distributing the square into a binomial. You cannot do that. That breaks dear Aunt Sally's heart. What you have to do is write it out twice, FOIL it out, or distribute, and then you can apply power rule to each of the terms thereafter. Alternatively, if you write it out twice, you can use product rule. Either way, you get the same answer. Looking at the first one, I definitely would use the reciprocal identity for sure, and just get secant tangent. But if you did go through the quotient rule, you would get the same answer. All right, so what's the deal with both of those cases? The chain rule is better. It's better. It goes like this. More or less, this is the Leibniz intuition for it, but the idea is if you have a function inside of another function, what you would do is you would take the derivative of the outermost function, keep the innermost the same, and then multiply by the derivative of the innermost. You got to see this in practice before you judge it. The idea behind it, Leibniz notation does a great job identifying that. So if you have an inner function u inside of y, well, what the idea behind it is you can differentiate first with respect to u and then differentiate that u expression with respect to x, and these sort of like kind of cancel, and the intuitions there is it's that dy over dx is the same as the expression prior. So the best way to learn is to do. All right, so if I were to apply these, so I don't expect you to be a master of it just off that 30-second rundown, the idea is this: to identify what is the outermost function and then what is the innermost function. By the way, for this one with 4, I probably wouldn't use chain rule on, but it's just to show that it works. For this one, sure, I would use chain rule on. So I would read it this way. I'd say, well, the outer function is this square. And then the inner function is the 3x plus 1. It's the line. So the way I would approach this based on the definition here is I would take the derivative of the outermost expression and keep everything on the inside the same, and then multiply by the derivative of inner. So I'm going to just go ahead and show this for 3. I'm going to, for 4, I wouldn't really do this rule 4, but the idea behind it is to show that, hey, this is a rule that you should trust. It works, because I'm not proving this rule. But the innermost function would be the cosine, and the outermost function would be like the 1 over x, 1 over whatever your function is. So it's 1 over, our u of x here, or our g of x here would be that cosine. And then the y, or the f, would be the 1 over. So I'm just going to show it, and then we'll build this like what's outer, what's inner intuition thereafter. But the idea is, well, okay, the outermost function for this one was that square. So I'm just doing power rule with that expression. I'm keeping the inside the same, and then I'm multiplying it by the derivative of the inside, the inside being just that 3. Derivative of 3x is just 3. And then I went ahead, I multiplied the 2 and the 3, distributed the 6 in, and I got the same expression that I got within the warm-up when I did it two other ways, really. And then within this expression, I rewrote this as the outer function being kind of more clearly labeled here as this to the power of -1, and then that inner function being cosine x. So I just did power rule on that outer function, kept the inner the same, And then I multiplied by the derivative of the inner, which is that negative sine x. So I brought the cosine back down. This is a little more work than you should do, but you get secant x tangent x, which is the same expression over here. Just verifying that indeed the chain rule is a thing. It's a good, useful rule. We're going to use it all the time now. But really, in real practice, I would just do, hey, this is secant. I know that definition. Okay, so if you want to practice, so we got to build the skill, right? So if you want to practice identifying what's the inner and what's the outer, do it right here, right now. All right, so yeah, give it a go. So identify the outermost function and then the innermost function. 3, 2, 1. Here are the answers. So for each of these, I put a u. You can ignore that if you want to. You could just say, hey, this is the outer. This is the inner. That's just fine. The reason why I chose to use u is just based off of this little Leibniz expression that I kind of wrote earlier. So looking at the first one, yeah, secant is clearly on the outside, and then inside of secant is the 3x. Here, it's a little harder to see with exponentials, so sometimes people write the exponential this way when you have a lot going on up in the power, but the exponential is definitely the outer function, and then the inner function's cosine. So it flip-flops within 7, right? Inner is being cosine, or outer is cosine, and then inner is the e to the x. Looking at 8, we have the cubic on the outside, and then on the inside is the line. So this is kind of like a baseline case. Okay, and then looking at 9 and 10, these are kind of trickier cases to look at. Reason being is that it's a little difficult to see the square as the outer function, but what I like to do is when I see an expression like this, I think of it written in this way. This is just like notational conformity. Like we just decided as a math community that you can write sine of x all squared as sine squared x, which is different than sine of x squared. And it's kind of there's a little bit of a story to this, more or less. The story being that sometimes it's notation that makes a concept hard, not the concept itself. So just learn notation being the way we write math. So anyway, these are equivalent if you didn't know. So the outermost is the square, the innermost is the sine, and then it vice versa as it switches out for 10, the inner being the x square and then the outer being sine. Okay, so see if you want to practice. So all right, now we're in the rounded practice phase. So that's the idea. Let's just go ahead and apply it to a few different rounds. Give 9 and 10 a go. And 11 and 12 just use a definition. So if you have any comfort with those, feel free. But give 9 and 10 a go for sure. 3, 2, 1. Here they are. So outer function was that fourth power, the quartic, and then we kept the 5x plus 1 on the inside the same. So we brought that up front, and then we multiplied by the derivative of the inner. So that would just be the 5, right? Derivative of 5x plus 1 is just 5. So multiplying out the 4 and 5, you get 20. And this is a great final answer. I don't think you need to multiply out this 5x plus 1 3 times. That's a total waste of time. This is totally fine. Same thing within this one. Outer function is the square. Bring it on up front. Subtract that 1. Keep inner the same. And then the derivative of the inner is this expression. Likewise, I don't think it's worth multiplying this out. I think it's a waste of time. All right, looking at 11 and 12, these look like they're hard problems, but they're not too crazy. If you're looking at taking the derivative h prime of h1 here, the 2 is going to sneak on up front. Same exact way as how the 2 here snuck up front. And then we kept the inner the same. And then we multiplied by the derivative of inner, and the derivative of f being f prime. We're looking for the derivative at 4, and we have all this information, which looks super overwhelming. But really, I'm just looking at this input of 4, and I'm just finding f of 4 and f prime of 4. So f of 4 is just 4, and then f prime of 4 is 2. So it's 2 times 4 times 2. 2 times 4 times 2, and that comes out to 16. Looking at 12, we do have an f and then a g, so g is inside of f. So we take the derivative of the inner, or outer, and then we keep the inner the same, and then we multiply by the derivative of the inner. So this is going to be f prime of g of 3 times g prime of 3. So g of 3 is right here, it's 4. So this expression right here is 4, so we're doing f prime of 4. And then g prime of 3, that's right here, so that would be negative 1/2. So I'm doing f prime of 4 times this negative 1/2, so that'd be 2 f prime, hello, f prime for, yeah, so 2 times negative half is negative 1. So using the chain rule via a table. So the definition does not change. It's actually just even more explicit or direct use of the definition if you think about it. All right, so let's throw some radicals and rational expressions in the mix. I suggest utilizing rewriting the either radical expression or the rational expression. So radicals over here, rational expressions, being like fractions, writing them as an exponent first, then applying the chain rule. So give them a go. 3, 2, 1. So like within 13, I can rewrite the square root as power of 1/2. And as soon as I rewrite it this way, it starts to feel like these situations, right? So what we're doing right now is we're building up to more challenging scenarios because the chain rule kind of opens up some doors. So we see the 1/2. We bring it on up front. We subtract 1 from that to get negative 1/2. And then we take the derivative of the inner, which is negative 2x. The 2's happen to cancel, so be mindful of like order of operations. This 9 minus x squared is inside of the radical or inside of this negative 1/2 power. So you can't really do much to simplify with this expression, but the 2's do cancel, right? This is just a 2x sitting up top. This is a 2 sitting down below if this were to be a fraction. So 2's can cancel. This is how you can rewrite the expression. X here for the ride, negative here for the ride. And then this expression, the 9 minus x squared, can be rewritten down in the denominator as a square root. Looking at 14, this is just 1 over this expression. So that's the same thing as this expression to the negative 1/2. Bring it on up front. Take the derivative of the inner right here. And remember to subtract 1 from that power. So 2's up top, negative's up top, bring this down below, and you get this expression. Nothing cancels, so you can't cancel this 2 and 2 because this coefficient of 2 is inside of the square. So if that's like obvious to you, great. That means that you know algebra. But I have been doing this for a little bit of time, and I work with students that maybe forgot some algebra. So, PEMDAS, right? Please excuse my dear Aunt Sally. Or know your order of operations. This 2 is inside of a square. You cannot cancel these 2's. You'd be surprised. You'd be surprised. All right, looking at 15. Bringing up this 1/3 up front, subtracting 1, you get negative 2/3. Keep inner the same, and then multiply by derivative of inner. This is honestly fine. Like every teacher's different. I'm kind of cool with you leaving your answer this way. There's nothing to simplify. Like you could look to see division of 3 with this expression. Like this is a 21. If this were to be like a 9 or something, you can divide that out. You can, factor out a 3 here, but you can't. So I just left it as is in terms of the numbers, right? In terms of rewriting it to this expression, I brought this down in the denominator and wrote this as, the cubic root of that expression squared. And the 3's there in the denominator as well. It comes with the ride. This is up in the numerator because it's to the first power. But both of these are fine, in my opinion. Okay, looking at 16, you can rewrite this expression as the 1 minus x squared all to the negative 1/2. So this is algebra. Bring that up front, subtract the 1, keep inner the same, and multiply by derivative of inner. The 2's cancel, the halves cancel, and then you're left with just this lone x up in the numerator. The rest of the expression can go down below, rewriting that rational exponent as the square root of the thing cubed. Was that a little fast? I mean, use pause, right? And really study. I mean, the way to be a good kind of math student is to understand each equal sign, every equal sign, going from here to here, or from, derivative to here, or from this algebraic step to this algebraic step. So if at any point you're confused about how did he get from here to here to here, feel free to ask, let me know. Okay, we got trig, we got exponentials, we got logs. Give these a go, 3, 2, 1. So we're just throwing in those other derivative rules. Tangent of pi x, outer is tangent, inner is pi x. So derivative of tangent is secant squared, and then multiply by the derivative of the inner. That's just a power rule. It's just a coefficient of this x. It's as if it was like 3x, and the derivative just being 3, the slope. So here it's pi. Derivative of constant, 0. Over here, I rewrote this as cosine x all squared. Rewrote it as cosine x all squared. Brought that 2 up front, kept the inner the same, and then derivative of cosine's negative sign. So the negatives cancel there. Over here with the log, so it's going to be 1 over this expression, and then derivative of the inner is 18x squared. And you can simplify that because you have the 18x squared up top, 6x cubed down below. 18 over 6 is 3, and then x squared over x cubed. X down below. Last one, the exponential stays the same, right? Because the derivative of e to the blah is e to the blah. That's how I kind of say it. But then, what is your blah? If your blah happens to be a function, well then you need to use chain rule. And in this case, it's a chain rule scenario. So derivative of blah here is 2 cosine x, and that's just going to be multiplied on the side. So sometimes people rewrite it this way. Okay, another round 4. Okay, so yeah, let's start to marry some ideas together. So we already know we've been applying the power rule and chain rule together, but what about the product and quotient? They're still things, right? So you're gonna need those rules. That's my hint. 3, 2, 1, here are the answers. All right, so you can see here in purple, I've like highlighted like the exact like what rule is in what rule. So this happens to be a chain rule inside of a product rule. So as you work through the product rule first, because that's the outermost rule layer, you're doing derivative, or you're doing keep first, derivative of inner, blah, 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 blah. Let's restart that one. Keep first, derivative of the second, and then within that second one, you have an inner function. So that would be chain rule. So this is where you're using chain rule within this step right here. So derivative of outer is just that cosine, derivative of inner is just that 2. Keep the inner the same. Plus derivative of the first, and then keep the second. So that was a chain rule that occurred within a product rule. You can clean it up if you'd like. In this case, this is a quotient rule as like the larger rule, and then inside of it is a chain rule because the numerator has binomial squared cubed. So looking through this one, we're going to do low, d high, so within the d high, derivative of high, that's your chain rule, minus high, and then d low, and this is all over low squared. And if you want to simplify that, you can. Within 23, you got a product inside of a chain, so it flip-flops, right? 21 was chain and a product, and then 23 is a product and a chain. Because first rule you're doing right away is a chain rule. E to the blah, derivative of that is e to the blah. And then is blah a function? It sure is, and it's actually a product of two expressions, so you have to use a product rule within that chain rule. So, you know, the derivative of inner being derivative of x times secant x is this expression right here, using the product rule. And then this one's just a mess. I actually think the better way of doing this is to cry. All right, moving on. No, this is just me being extra. So yeah, can you use a log rule though to make this easier? I think you totally can. A log property, all right? Yeah, you can use a log property. This is crazy. I wouldn't do it this way for the record, but I wanted to show this process. What I would do is I would, so you have the log of a quotient. If you have a quotient inside of a log, you can rewrite that as subtraction of the 2 logs. So this is log of this minus log of that. That's a better way of doing it, and then at least you don't have to deal with a quotient rule inside. But this way is totally viable. So I did 1 over the inner function, because that's the derivative of log x. And then the inner expression happens to be a quotient, so I did a quotient rule. Yuck. And then I cleaned it up doing algebra, but that's a bit much. Okay, try out round 5. This is the last one. How are we doing on time? Not bad, not bad. So yeah, I heard you like chain rules, so I put a chain in your chain so you can chain while you chain. Yeah, so you need chain rule multiple times here. There's a function in a function in a function. That's my hint. Give it a go. 3, 2, 1. All right, looking at 25, you'll notice that it is technically an x minus 1 inside of a square inside of a e expression. This is a very funky looking expression. This is actually the expression for like a normal curve, by the way, like a bell curve. The innermost is x minus 1. The middle function's the square, and then the outermost is the e to the blah. And this is just a coefficient. It's just like the number 3 sitting up front. So you have this 3 sitting up front, or whatever it is. Derivative of e to the blah is e to the blah. And then derivative of the middle is bringing out this 2. The 2's cancel. You get this -1 coefficient. And then x minus 1 is there. And then derivative of the innermost layer is technically 1, because the derivative of x is just 1. So I would just be chilling off to the side here. But, you know, it's not necessary to write times 1. This one, very clearly a function in a function in a function. I would say innermost being 3x minus 6, middle being cosine, and then outermost being the radical, which is power of 1/2. So the way we work this out, so this is a good chain in a chain here, or function in a function in a function. The chains are like the meats, and then the functions are like the buns. So this is like a good old, I don't even know. What's a hamburger? What is the double stack or Big Mac? I don't know. I don't go to McDonald's that much. That's when you have like a bun, then meat, then bun, then meat, then bun, whatever it is. That's what's going on here. So we're going to go 1/2 up front, subtract the 1 and for the power, keep inner the same. So then you take derivative of inner. Okay, well, if I were to take the derivative, what I like to do is I like to pick up this cosine 3x minus 6. And what if I were to just like off to the side take the derivative of just this expression? What would that look like? Well, anyway, it would look like this. Derivative of cosine being negative sine, keep inner the same. And then now we have this innermost layer. What's the derivative of 3x minus 6? It's just that 3. All right, last two here. These are like the bonus rounds. If you can handle these, good for you. Here we have a product rule is the outermost expression, so I run through product. These are totally bonus. I'm not going to talk too much about them. And then within the product rule, for the derivative of this right expression, this right factor, which I wrote out here, is a function, the square, inside a function, secant, inside a function, e to the blah. So it's e to the blah times derivative of this secant of blah, which is secant blah, tangent blah, and then derivative of the innermost blah, which is this expression. Gross! And then 28, just for fun, is, and this is what I mean by taking the derivative of like an expression kind of off to the side. So I did the outermost function. I kept inner the same. When I saw that inner, which is like a middle in some ways, I did quotient rule. And then when I encountered that sine squared of 4x, I just wrote it off to the side here. And then that was just that little piece. We love calculus. Yeah, that's it. We love calculus. That's all for today. Math on.